This lesson is entitled Introduction to the Derivative. Earlier, you may have studied average and instantaneous velocity. We'll take a moment to review this topic, and if you've not studied it before, this will help familiarize yourself with the topic. Consider function s of t equals 3t squared. S stands for distance, t stands for time, and we're interested in studying this equation from time 0 up to time 4. Now, we're not including units with the time here. Later, when we study velocity, that will be more important, but for this topic, what we're doing with this does not require that we address units, so we won't. Now, average velocity is something you probably have had before getting to calculus. It's simply the slope of the line joining the initial point of the graph with the final point of the graph. That is, in this case, t equals 0 to t equals 4, or the ordered pair 0, 0 to 4, comma, 48. And so the slope of that line is called the average velocity. In this case, it'll be 48 minus 0 divided by 4 minus 0, which is, of course, is 48 over 4, or 12. So that's the average velocity. Instantaneous velocity, on the other hand, is what we're interested in, and it involves a bit more thought and work. First, you have to recognize that instantaneous velocity is not the same at each point. Okay, graph. Secondly, you must accept the fact that a curved line has no specific slope. You can't look at a curved line and say the slope of the curve is, because it's not uniform. The best one can do is to describe the slope of a straight line tangent to the graph at a point, and that will be equivalent to the slope of the graph at that point. Let us consider our same example, s of t equals 3t squared, and let's find the instantaneous velocity at time 2. And we will use that same point slope formula, m equals y2 minus y1 over x2 minus x1 to achieve our ends. What we're going to do is we're going to use the fact that we talked about this earlier in this course, that a straight line is nothing more than a curved line is nothing more than a lot of little straight lines in succession. So what we're going to do to find the slope at 2, which is going to be the instantaneous velocity, we're going to find the slope of a small part of the line segment near 2, point t equal 2. So what we're going to do is we're going to pick up a point close to t equal 2, and that's going to be t equal 2.1, and we're going to find the slope of that small line segment. And what we're going to do is, of course, this is our function, so it's s of 2.1 minus s of 2, that's your y2 minus y1, over 2.1 minus 2, that's your x2 minus x of 1. Of course, s of 2 plus 1, 2.1 simply means put 2.1 into the function and do the arithmetic. And of course, s of 2, same thing, put 2 in for t and do the arithmetic. So that's what we have done here. And of course, the difference here of 2.1 and 2 is 0.1. So we'll find this difference, divide by 0.1, and we get approximately 12.3. Now, this is not the true instantaneous velocity. It's an approximation of the instantaneous velocity at t equal 2. if we wanted a closer approximation, then we would need to take, instead of 2.1, maybe 2.01, or even better, 2.001. That would give us a closer approximation of the instantaneous velocity at 2. Now, on the other hand, if we wanted the instantaneous velocity at 3, we would have to do the problem all over again, this time picking a number close to 3 and finding the slope of that little line segment. When I say close to 3, I mean 3.1 or 3.01 or 3.001 or the like. So this might sound to you to be somewhat an amount of work, and it is. And then you might say to yourself, there must be a better way, and there is, and a better vehicle, and there is, and that's what this lesson encompasses. Let's consider 2.1 again and think of it as 2 plus 0.1. And 2.01 is 2 plus 0.01. And 2.001 is 2 plus 0.001. Now, let's think of 2.1 as another way of being 2 plus h, where h is 0.1. Or 2.01 is 2 plus h, where h is 0.01. Or 2.001 is 2 plus h, where h is 0.001. That seems reasonable. Now, h is getting smaller and smaller. In fact, what is h approaching? It's approaching 0. But h cannot be 0, because if it is, then our denominator is going to be 0, and that can't be. But let's rewrite our formula for instantaneous velocity, which we did earlier, the other page, and let's write this s of 2.1 instead of s of 2.1, s of 2 plus h, minus s of 2 over 2 plus h minus 2, okay? In other words, we're writing s of 2.1 as s of 2 plus h, where h is 0.1. So what we're going to do is say, let the limit of h be 0.01. So that's saying the same thing here. The limit of this, if you substitute in for h, 0.01, gives you the same thing. These two quantities are the same. Now, if we wanted to do it for 0.01, then we would have to change this h approaches 0.1 to h approaches 0.01, and so on. Well, is there any reason we couldn't, since h is approaching 0, is there any reason we couldn't just write this and just say it what it is? H is approaching 0, and we will. Now, that's a major breakthrough. That line right here is a major breakthrough in the history of calculus to getting us what we desire. So let's consider example 3t squared and find the instantaneous velocity t equal to using this formula right here. The limit of s of 2 plus h minus s of 2 over h as h approaches 0. That's simply the formula we had at the bottom of the previous frame. So what does s of 2 plus h mean anyway? It means come up here to your s function, and everywhere there's a t, put 2 plus h. What does s of 2 means? It means come up to this s function, and everywhere there's a t, put 2, all over h. Now the rest of this problem is just a matter of arithmetic and algebra. Let's square this quantity. When we do, when you square 2 plus h, square the first term, 4, multiply the 2 together and double, 4h, square the last term, h squared. Minus 3 times 2 squared, all over h. That's all we've done is squared the 2 plus h. Now let's distribute the 3 here. Through here, they'll give us 3 times 4 is 12. 3 times 4 3 times 4h is 12h, and 3 times h squared is 3h squared. And of course, 2 squared is 4 times 3 is 12. Okay. Now let's subtract 12 from 12. We can do that. That comes out nicely, so we do. And now we notice that each of these terms has an h in it. So can we not factor out an h? And 3 is a factor of 12 and 3, so let's factor out of this expression 3h. And when we do, we get 4 plus h over h. Now we still have a problem in here. We can't substitute h because h is in the denominator and it's 0, and that can't be. But look, in the spirit of limits, which we've talked about for some time now, h is not 0, h is approaching 0. If h is 0, we can't cancel these h's, but if h is close to 0, we can cancel them. So h is close to 0, so let's cancel them, leaving us with this. And now pick a number close to 0. Well, is there any reason we can't just pick 0? I mean, the problem, we couldn't pick 0 here, but there's no reason we can't pick 0 here, so we will. And that means this thing becomes 3 times 4 plus 0, or 3 times 4 is 12, and that's our answer. That is the instantaneous velocity, and that is the exact answer for the instantaneous velocity. Now, one last consideration or question. What if t were 1? Well, if t were 1, then what we've got to do is go back on this problem, and everywhere we have a 2, we have to put a 1 and do all the arithmetic and algebra. What if t were 3? Again, we have to go back, and everywhere there's a 2, we have to substitute a 3 and do all the algebra and the arithmetic. Well, is there any reason we can't just, since t can be 1, 2, or 3, let's just call it t. Let's just call it what it is, t. And what is s of t plus h? Well, s of t plus h means go to our function, and everywhere we have a, we're going to put in t plus h for the variable, okay? And this will be minus s of t, which is substitute in. Now, square this, which is t squared plus 2th plus h squared. Okay, we didn't do anything to this. Now distribute to 3. In other words, multiply everything by 3. And notice we have a 3t squared and a 3t squared. The 3t squareds cancel. And look, we have a 3 here and a 6 here. Can't factor out a 3? And we have an h and an h squared. Can't we factor out an h? And so we will factor out a 3h. And when we do, we are left simply with 2t plus h. We still have this burdensome h in the denominator, but look, we're approaching 0. We don't get to 0, so we cancel these two h's, and we're left with just 3 times t plus h. Now, let h become 0, and you have 6t. Now you say, what does that mean? That means that the instantaneous velocity is 6 times t, whatever t is. Now, if t is 2, what is it? It's 12, which is what we got for t equal 2 when we worked it out. But this means we now know what its instantaneous velocity is going to be when t is 1, t is 2, t is 3, and whatever, as you see here. That means all we have to do is multiply the t times 6 in this particular problem to get the instantaneous velocity. Now, this is really nice because not only are we having to do not all of the arithmetic and pick value after value to get closer and closer, and then do it all over again with some other number, we have a way to do it and get an answer that gives us the instantaneous velocity for that particular problem. And it's not just an approximation, it's the exact answer. Early mathematicians realized that they had more than just instantaneous velocity. They had actually the instantaneous change along any curve, not just a distance curve. It can be anything, y in terms of x. And what they have is a change in y per change in x. So it's not just change in distance over change in time, which is velocity, but we can relate it to the change of anything of one variable in terms of the other variable. And this is where it really comes in for us in calculus. Now, there is a symbol that we're going to use. We call this the derivative, by the way. We mentioned this again early in the course. A derivative is a byproduct of some other process. In this case, it's basically a byproduct of the fact that we know how to find the slope of a straight line. And a curved line is, in essence, a lot of little straight lines. And so we can find the slope of a little straight line. And this is what we've done. And this is called the derivative. Its symbol is f prime of x. That's the notation we're going to use in this lesson. It's not the only notation. Other notation will be revealed to you soon in this series of lectures. So here's the definition of the derivative in terms of f of x. It's given a function f of x, f prime of x, which we're calling the derivative, is the limit of f of x plus h minus f of x over h as h approaches 0. What this means is, if you're given a function, you know f of x, you're given that. You find f of x plus h by putting x plus h in substituted in for x in the function, and then do the algebra and do the arithmetic. Let's take an example. If you're given the function f of x is 3x squared minus 2x plus 5, find f prime of x. Well, we have the function that's given to us. We have to find f of x plus h for ourselves. Well, that's nothing more than everywhere there's an x, put x plus h. So I have x plus h, so that's 3x plus h squared, minus 2x, so that's minus 2x plus h plus 5. Substitute in to our formula from back here. You got to know this formula. You're going to have to. Practice will make it a part of your vocabulary. So we substitute in for f of x plus h this, and subtract from it f of x over h as h approaches 0. Okay. First thing I'm going to do is I'm going to square this. And that's all I'm doing to this line. The difference between this line and this line is I've squared x plus h. And now I'm going to multiply everything by 3, everything here by minus 2, and everything here by -1 makes that -3x squared. Minus a minus is a plus, minus a minus is a plus. And then I'm going to, I see that I have a 3x squared and a minus 3x squared, so they're going to vanish. I see that I have a minus 2x and a positive 2x, so that's going to vanish. And I have a 5 and a minus 5. They're going to vanish. So the only thing left here is the 6xh plus 3h squared minus 2h over h. Now, I can factor out from this an h. That's a common factor, leaving me with 6x plus 3h minus 2, all over h still. Now remember, h never reaches 0, just very close to 0, so I can cancel these h's out, leaving me with just 6x plus 3h minus 2. Now substitute in for h 0, and I get 6x minus 2. And what that is, that's the slope. That's the rate of change at any point on the graph 3x squared minus 2x plus 5. It's 6 times the x coordinate minus 2. So when x is 1, that'll be 6 times 1, which is 6 minus 2, or 4. When x is 3, this will be 6 times 3 is 18, minus 2 is 16, and so on. Now, before we leave this problem, you see this string of asterisks, these like stars. I have 5 of them here. That means this line is pretty important. I want to say something about it. It's line 3, 1, 2, 3. In this line right here, everything that doesn't have an H should and must vanish. 3x squared doesn't have an H, minus 3x squared doesn't have an H, and they're opposites. The 3x squared vanish. Minus 2x doesn't have an H, plus 2x doesn't have an H, they're opposites, they vanish. 5 doesn't have an H, minus 5 doesn't have an H, the 5's vanish, leaving me, and everything left must have an H in it. Now let's stop and think. It's take a while to do this, but let's do it right and think. What we've got to do is get rid of this H. So everything up here must have an H in it so that we can factor an H and then cancel. If everything doesn't have an H, I can't factor an H and I can't get rid of this. But it always will work out if you've not made an error, so that the non-H terms will vanish and everything else will have an H, and you factor out an H at a minimum. Okay. And that's what makes this problem work. Now, if it doesn't happen that everything that doesn't have an H doesn't vanish, you need to go back and check your algebra. And you can make mistakes. For example, some students don't put parentheses around here, and when they get to this term, they just say that's minus 3x squared minus 2x plus 5, and it doesn't vanish. Because you have a 5 and a plus 5, you get a 10, you don't get rid of it. And you have a minus 2x and a minus 2x, you minus 4, you don't get rid of it. What is your error? Your error is there's a minus sign here, which says, hey, this is not negative 2x, this is plus 2x. This is not 5, it's negative 5. So you must be careful. Or suppose when you square this, you don't square it correctly. Okay. All of this is important. All of this is important. That's a well done problem, I think. We've shown far more steps than you need to, but you'll have to decide which steps that you can omit. You will notice one thing, and I want to emphasize this. We talked about this early in limits. You do not drop the limit notation, the LIM, until you get to the point where you sub in. See, I haven't subbed in for H equals 0 here, here, here. Even here I haven't. Then I'm subbing in and I get, so I can drop it. Okay. Please make sure you abide by that. That's important. Let's look at example 2. Now, example 2 is x cubed. X cubed. We don't have anything hanging on to it, so this is rather short problem. Well, we have f of x plus h is x plus h cubed. So we fill into our formula f of x plus h cubed, minus f of x, that's x cubed, over h. Now, what we have to do is cube this. And you'll probably just want to go square it and then take that answer and multiply that by x plus h. That's what we've done here. There's a way to expand a binomial, but let's not take time to do that. It's so easy just to multiply x plus h by itself 3 times. And when we do, notice the x cubes vanish. And then we have an h, an h, and an h. So let's factor an h. We do. We cancel these, and now let h go to 0. And this becomes 0. This becomes 0. 3x squared is our answer. In other words, the slope. Anywhere on the graph, x cubed is positive except at 0 where it's 0. For any other, it's positive because you're squaring the x. Okay? And if you look at the graph of x cubed, I think you'll see why it's positive everywhere but at 0. Now, one other thing I want to say before I leave this particular problem, if this were x to the 5th, it gets a little cumbersome because we're going to have to multiply x plus h by itself 5 times. What if it were to the 10th power, x plus h to the 10th power? That's a lot of work. But there's good news further down the road that will help us out, but it doesn't occur in this lesson. For that, we don't have to worry about it because we don't have x to the 5th. When we get to the point where we have x to the 5th, we will have a better way to do this problem. Let's look at what happens if you have f of x is 1 over x. In other words, what do you do when x is in the denominator? Well, first of all, we have to find f of x plus h. That's your first step. Second step is plug into your formula, so you need to know your formula. And now what we're going to do is we're going to get a common denominator, which is x times x plus h. So that's what I have, common denominator. Now, what did I do to this x plus h to get the common denominator? I multiplied this denominator by x. Well, you can't do that, but you can if you do it to the numerator. And when I multiply x times 1, I get this x. And this has an x, but I need an x plus h, so I'm going to multiply it by x plus h. But I can't do that, but I can if I multiply this by x plus h. That gives me this. Now, we have common denominators, so let's put it all over one common denominator here. So that becomes x minus the quantity x plus h, all over this, all over h. Now, dividing by h is the same thing as multiplying by 1 over h. So if we multiply this by 1 over h, this gives us this. Now, let's drop the parentheses. So this is x minus x. So the x's disappear. This is a minus h. These h's cancel, leaving us minus 1. And now we'll substitute in 0 for h, and it's minus 1 over x times x, or minus 1 over x squared. Fractions have to be done like this. You might, whenever you get to somewhere along this, just automatically, realize that this h is going to always go here. See what happens? And what we do, the only difference between these two terms is this h. This is this term right here with the h put there. See if you can't figure out how you can just go from, say, here down without a lot of fanfare. That's our answer. So the slope of this graph is going to be always going to be negative. And if you graph it, we're not asking you to, and we're not going to graph it for you, but I think you'll see why the slope is always negative if you look at the graph. Example 4 is a radical, a square root. So f of x plus h is just the square root of x plus h. We substitute into our definition, and we get this. And now what we're going to do is we're going to multiply the numerator and denominator by the conjugate of the numerator. Remember what a conjugate is? A plus b and a minus b are conjugates. We had a problem back in the section. If you have not seen that, it was on finding limits when you're given an equation. We had an exact problem where you had to multiply numerator and denominator by the conjugate of the numerator. The reason we did that problem back then is because we knew this was coming. Okay? And so that's what we're going to do, is multiply the numerator and denominator by the conjugate of the numerator. And when you multiply conjugates, it gives you this thing squared. Well, when you square this, it just lifts the radical. And when you square this, it just lifts the radical. And then we have it, just copy the denominator. Don't do anything with the denominator, just copy it here. Now the x's disappear, leaving us with an h. these h's cancel, okay? And so now all we have is 1 over the square root of x plus h plus square root of h. Now, let h become 0, and when you do, this becomes 1 over the square root of x plus 0, or square root of x, square root of x, square root of x plus square root of x is 2 square roots of x, and that's your answer. When you have radicals, you do this. Now, if this were a cubed of x, it would be done somewhat the same way, but it's a much, much more difficult problem, and we're not going to do it with you because there's going to be a better way coming. What we're trying to do here is we want you to understand what's going on, and we need this definition to get the good news later. We cannot get the good news later without this definition. And we're going to do that quite often in calculus. To get the good news for the derivative, finding the derivative, we're going to have to access the definition of the derivative. So it's not going away. Okay. Example 5 is, what do you do when you have 1 over the square root of x? Well, that's a combination of a fraction and a radical. F of x plus h, I think you can see, will be 1 over the square root of x plus h. So we'll fill in. All we're doing here first, see, we're always finding f of x plus h, and then we're filling into our formula. And then that's really, we're done. We can kind of, we being myself, the instructor, can kind of wash my hands of it. You now use the tools that you have had in other classes to bring the problem home. What I'm going to first do is going to get a common denominator, and that's x times, it's the product of the two denominators. Okay, well, to put a square root of x here, I've got to put 1 up here, and to get a square root of x plus h here, I've got to put 1 here. Okay, all of h. And now what I'm going to do, this is nothing more than this part right here, and I'm going to multiply the numerator and denominator by the conjugate of the numerator, which is square root of x plus square root of x plus h. And when I do, that's going to give me this thing squared, lifts the radical, minus this thing squared, lifts the radical, and then just copy this whole smear of the denominator. That's all I've done here, is I have done anything with it. Now the x's disappear, and I have a negative h, and that cancels, giving me negative 1. And guess what? I've gotten rid of my problem. So let's just let h become 0. And when we do, that means this thing becomes square root of x times square root of x itself. And this becomes the square root of x plus the square root of x itself. And the square root of x times the square root of x is x. And the square root of x plus the square root of x is 2 square roots of x. And that's my answer. Now that's a very involved problem. If you're a typical student, you're following this, but you're not ready to do it on your own. You need some practice. You need some practice. But what we've shown you here in these 5 problems are all the basics. Actually, 1 and 2 was when you have a simple polynomial. And then 3 was when you have a fraction. 4 was when you have a radical. And 5 is when you have a combination of a fraction and a radical. And the only thing you can do is work these problems, maybe have the answers in front of you and go as far as you can, and then peek back until all of a sudden you're doing the problem on your own. Now for 2 special examples. Kind of reluctant to give these 2. They're so easy, but we're giving them for a purpose. Let's take a function you're familiar with. This is a linear function, 3/5 x minus 7. We know what the slope is, the slope. This is y equals mx plus b. M is the slope, m is 3/5. We know, without using calculus, what the slope is. But let's do it by calculus anyway. F of x plus h, if this is f of x plus h is 3 times x plus h minus 7. Substitute into our formula this here, and subtract all over h. multiply by 3/5 everything, minus 7, minus 3/5 plus 7. 3/5 x and minus 3/5 x disappear. The 7's disappear. I'm left with 3/5 h. The h is canceled. I'm left with 3/5. The limit of a constant is this, so the limit is 3/5. Now remember, we have found the derivative. What is derivative? Is slope. This is slope. This is slope. What we've done this, the reason we've done this problem is so that you will know we're not getting a close answer. A lot of students, I think, because we're using this limits and taking a number close to 0, that we really have, are we really getting the really exact slope for the problem? And yes, we are. Look, we know this is the slope without calculus. Calculus tells us we get, and it's the same answer. It is the exact answer, and it is the exact answer. And that's why we worked this problem. And we worked one more, which is even more trivial, and that is we took something like y equals 11. That's a horizontal line. What's the slope of a horizontal line? 0. So f of x is 11. Let's think of f of x as not only being 11, but it's 0x plus 11. That means f of x plus h is 0x plus h plus 11 minus f of x. Now, if you'll notice, this is going to give us, this will be 0, and this will be minus 11, and we're left with nothing but the 0. And of course, the limit of 0 is 0. So we know the slope of a horizontal line is 0, but calculus shows us that it is as well. You see, calculus will do everything that algebra will do. But algebra cannot do everything that calculus can do. Calculus can find the slope of a curved line at any point and the slope of a straight line. Algebra can find the slope of a straight line, but not the slope of a curved line. And this is important that this be embedded. Calculus is algebra made stronger, okay, strengthened. And here we just, why did we emphasize this? Why did we do these two problems? And that is to show you that you really are getting the slope, the true slope, when you use the calculus. We conclude with an alternate formula for the definition of the derivative. This is important because it appears in textbooks. It allows you to find the derivative at a point. What we've been finding is the derivative for any point. So if your instructor gives you an equation and asks you to find the derivative or slope for 10 different points, you want to do what we just did, find an answer in terms of x and then put in each of the 10 different points. But if you just want it for one point, there is an alternate definition, and it is this: given f of x and some point x equal a, then the derivative at a, f prime of a, is the limit of f of x minus f of a over x minus a as x approaches a. This is a special formula, special form. I would think of it as being a corollary. A corollary is usually a special case of a theorem. Okay. Let's look at one example. F of x is 5x squared, find f prime of 2. So we're going to use this formula. F prime of 2 is the limit of f of x minus f of a. Remember, a is 2, so it's f of 2 over x minus a. A is 2. And so f of x is 5x squared, and f of 2 is 20, okay? And so that brings us to this point. We still have a problem here because we can't put in 2, but we can factor to 5, which we do. And then we can factor this thing, this is two perfect squares, as 5 times x minus 2x plus 2. And lo and behold, we can cancel this. Why? Because we never get to 2. Since we get close to 2, but never get to 2, so it's okay. These won't be 0. We cancel them, and then we just, it's 5 times x plus 2. And now substitute in 2 for your x, and the answer is 20. Now, we could have done this by using our other definition and do it the long way. And if we had, we would have gotten an answer, I believe, of 10x. And then we would have put in the 2, and that would have given us the same answer, 20. So we want you to be aware of this. Whether you use it or not depends on the problems that are assigned in your particular class. But we want you not to feel disadvantaged, because it is a fairly popular formula, but nowhere near as popular as the main definition, which we end with here. And this is the definition. We put it in a little light bluish colored box. That's how important it is. You must memorize this. You must be able to recite it, speak of it quickly, not a lot of thinking about it. It's got to be more or less a part of your vocabulary, because we're going to be using it in subsequent lessons. But for now, this completes this lesson.